The following content is provided by MIT OpenCourseware under a Creative Commons license. Additional information about our license and MIT OpenCourseware in general is available at ocw.mit.edu.
So today we're going to continue with chemical equilibrium. And at the end of the lecture, Professor Sayre will be here to talk about exam 2. So we're going to start off where we left off, and we are talking about Le Chatelier's principle. So Le Chatelier had this great idea that systems tend to respond to stress in a particular way, that if you apply a stress to a system at equilibrium, it will respond to that stress by trying to minimize the stress. So the reaction will respond to adjust for the stress that was applied and minimize that stress. So if you consider what stress is applied to a reaction and then how that stress can be minimized, you can predict whether the reaction will go in the forward direction or the reverse direction. And so it tends to go in one of those directions to minimize the stress until the stress has been minimized, and then equilibrium is reached again. So we talked last class about adding and removing products or reactants and how the system would respond. And today we're going to consider changes in volume to a gaseous system and also temperature and how systems respond. And at the end, we'll talk about the relevance of this to biological systems. So again, here's Le Chatelier. So we can use this to predict the direction of the reaction, the response to the stress that is applied. So first, let's consider what happens if you have a mixture of gases at equilibrium. They're reacting. Again, at equilibrium, it's a dynamic process. So you have the reaction going in the forward direction and the reverse direction, but the rates of those reactions are the same. So there's no net change in composition, but the reaction is still happening. So now, if you have a system at equilibrium, a gaseous system at equilibrium, and you change the volume, we'll consider how the reaction will shift to compensate for this stress. So a decrease in volume of the gaseous system will cause an increase in total pressure. How do we know that? What equation tells us about pressures and volumes of gases? Yeah. Ideal gas law. So PV equals nRT. So that's what we'll be considering today. So Le Chatelier's principle would predict that the system will respond in such a way then to reduce the total pressure. So if you decrease the volume, increase the total pressure, the system's going to respond then to reduce that total pressure, to minimize that stress that was added into the system. So let's look at an example. So here we have 2 P2 gas going to P4 gas. So 2 molecules of P2 going to 1 of P4. And in the middle one here, we have the system at equilibrium, and we're going to consider both what happens when we decrease the volume and when we increase the volume. First, let's consider this decrease. So what happens is that a decrease in volume shifts the reaction reaction toward products. So why is that true? Well, it has to do with the stoichiometry of this equation. So for every 2 moles here that are consumed, only 1 is formed. So a shift to the right toward products is going to reduce the number of molecules in the system and therefore reduce the total pressure. So when you have a decrease in volume, that initially causes the total pressure to increase, and so the system responds in such a way to minimize that stress and decrease the pressure, which it can do by shifting this reaction toward products or to the right. So this is what Shat-Liaised principle would allow you to guess when you look at this particular reaction, and you can also prove to yourself that this is correct by considering Q and K and delta G. So let's prove that this is what would in fact happen. So we consider again Q and K. Remember, this is what's important in both of these two lectures. We're talking about Q, the reaction quotient, the ratio of products to reactants under whatever condition you are at that particular moment in time, whereas K is our equilibrium constant, the ratio of products to reactions at equilibrium. So now to make the math easy, let's assume that the volume decrease happens by a factor of 2. So you decrease the volume by 2. So that's going to initially increase the pressure of both gases, of P2, the reactant, and P4, the product, by 2. So the partial pressure was going to go up. So now we can figure out by how much with this decrease in volume. So Q, again, the reaction quotient, is products over reactants. So our product, partial pressure of P4 over the partial pressure of P2 raised to the 2. So again, you consider the stoichiometry when you're writing your equation for Q or for K. So if we work this out, we find that by decreasing the volume by a factor of 2, Q is now half what it was. It's decreased by a factor of 2. So now Q is less than K. So we were at equilibrium before, but a stress was implied, the volume was decreased, and now we have a situation where Q is no longer equal K, Q is less than K. And so that's going to then shift the reaction toward products. It'll be spontaneous in the forward direction. So you can just sort of rationalize what will happen, and you'll have questions on homeworks and on exams saying, okay, if this stress is applied, predict how the reaction is going to respond. You can work it out in terms of thinking about Q and K, or just sort of rationalize how do you minimize that stress that's been applied to the system. And if you're asked how much happens, if numbers are given, you can actually work this out, what Q is at that point and what K was. Now, if we increase volume, so if we go in this direction, what's going to happen? Well, the reverse will happen in this case. So we're going to shift toward reactants. So for every 1 mole of product that goes in this direction, in the reverse direction, you'll form these 2 moles of P2. So a shift toward the reactants, a shift to the left, is going to increase the total pressure. So if you increase the volume, you're initially going to decrease the partial pressure, and a shift in this direction of the reactions will compensate. It'll increase that partial pressure until you reach equilibrium again, because you're going from, in the reverse direction, from 1 to 2 moles. So again, we could work this out in Q and K, and actually we'll do this at a later example, but again, you can rationalize or figure it out in terms of Q and K, and what delta G would be, positive or negative, which direction the reaction is spontaneous, in the forward direction or in the reverse direction. All right, so let's make this a little bit more complicated now and consider what happens when you add an inert gas into that mixture. So here we're adding an inert gas into the container, and when we add it, it's increasing the total pressure of that container, and temperature is constant. Add an inert gas, increase the total pressure. What's going to happen? to the reaction? Will it shift to the left or the right? What's going to happen? So the answer is, in this case, nothing. Why? Why won't this affect the equilibrium? Why aren't we affecting Q here? And the answer is that Q depends on the partial pressures of the gases involved. And partial pressures are not changing. The total pressure is changing, but the partial pressure of those gases are not changing. So at this point, let's review partial pressure. And then I think this will make a lot of sense. So the definition of partial pressure is the pressure that each gas would exert if it were alone in the container. So here we have some oxygen at 1 atmosphere. Here we have nitrogen at 1 atmosphere. And here we have a mixture of the oxygen and the nitrogen. And now that we've added one gas to the other, the pressure is 2 atmospheres. So we added 1 atmosphere of this and 1 atmosphere of that, and we have 2 atmospheres total. But if you're asking about the partial pressure, say, of oxygen, the partial pressure of oxygen is the same here as it is in the mixture, because partial pressure is the pressure that's due just to that particular gas, as if it were alone in a container. So let's look at the equations for partial pressure. And if you haven't had partial pressure before in high school, I said this is a review, but this is actually everything you need to know about partial pressure for this unit, so it doesn't really matter if you haven't seen this before. So if we have our familiar ideal gas law, the partial pressure of A depends on just the number of molecules of A in that container at a given volume. The total pressure of a system will be the partial pressure of A plus B plus C, depending on how much of a mixture you have. In this case, we have a mixture of O2 and N2, so our total pressure is 2, but our partial pressures of each of these gases in here is still 1, as it was before when they were alone. So how is this all relevant? Well, it's relevant because Q depends on the partial pressure, not the total pressure. So the question you have to ask yourself in looking at all these problems is the partial pressure changing, i.e., is Q changing? Because only when Q changes will equilibrium be affected. So in the particular example that I gave you at the beginning here, we asked what happens if an inert gas is added to a container, increasing the total pressure at constant temperature. And so the answer was nothing, because Q is not affected. The partial pressure for the gases is still the same. The volume hasn't changed any. You haven't added more of these two gases. You added an inert gas. So the number of moles of these are the same. The volume is the same. So the partial pressure is the same. And if partial pressures are the same, then Q is unaffected. So Q does not change. So it doesn't matter. There's no shift. Q is still equal to K. We're still under these conditions. Seems like it's a stress applied, but it's not really a real stress, so there's no change. All right, let's look at another scenario and consider what will happen. So now, what happens if we add an inert gas, but the total pressure and the temperature are kept constant? So the total pressure is not allowed to change. It's kept constant. So for this to be true, for you to add two things together and the total pressure doesn't change, what had to have happened? Volume. Volume had to have changed here. Otherwise, this couldn't be true. So the volume had to change, because here we have, if we are constant temperature, we have the gas constant here, number of moles. If we've increased this number of moles, and then the total pressure has to be affected by it, if it didn't, that means volume had to have changed for that to be true. So for the pressure to be constant, the volume of the container must have increased. And so you'll notice in working a lot of these problems, often it won't say anything about the volume. It'll tell you about the pressure, and you have to figure out whether that means there was a volume change, because the volume changes are the ones that are relevant. So it's all sort of in the wordings of these problems. All right, so the volume must have increased. Otherwise, the pressure would have gone up. So then this question really is, what happens when the volume increases? And we know how to answer that question already. So for this particular reaction where you have these two P2s going to one P4, an increase in volume means that you're going to shift to reactants. You're going to go from this side that has 1 to this side which has 2. And that way, when you increase the volume, the partial pressure is going to drop. So you want to respond in a way to minimize that stress, which means you want then an increase in the partial pressure. And again, we can think about this in terms of Q and K. And let me just work a little example on the board to emphasize the point. So we did the other example earlier, but now let's consider if your volume doubles. And my picture doesn't make it look like it's doubling, but this makes the math easier. So that means if the volume doubles, you're going to half the partial pressure initially of both gases, of P2 and P4. And so now we consider Q, because it's really all about the relationship between Q and K. Q is going to equal the partial pressure of the products over reactants, and the reactant is partial pressure of P2, and again with the stoichiometry, that's squared. So if the volume doubles initially, the partial pressure will be half for the products, and also half for the reactant P2, and that's squared. So Q is twice what it was before. So now Q is greater than K, and so you will have a delta G that's positive, which means you're going to be spontaneous in the direction toward reactants. And you could sort of just reason that out by looking at the number of moles on one side or the other, or if you want to convince yourself, you can look at Q and K, because this is where it really comes from. So when Q equals K, you're at equilibrium. If it's greater than K, then you shift. Yeah, question?
When you put that 1/2 into the equation, is that just like a ratio that you're saying?
Yeah, just because it doubled, so we're saying that then this is, so there could be real numbers that you're looking at, but this is just considering if you double this, then you're going to have a decrease.
Double the volume and half the product.
The partial pressure. Yeah, so it's the partial pressure. Yeah, the number of moles aren't changing, but the partial pressure is changing because the volume is changing. All right, yeah.
Just because we get Q what it used to be, that doesn't mean it's greater than K, does it? Not necessarily.
So Q, well, at equilibrium, Q is equal to K. So the Q and K are both products over our reactants, or the partial pressure of products over reactants. So when you make some change like this, Q was equal to K, but now you have a change, either if you increase or decrease, then it changes the relationship to your equilibrium. So you're no longer under the equilibrium conditions.
Are we given that Q is equal to K in the initial states?
So at equilibrium, Q equals K by definition.
Right, but are we given that in the question?
Right, so you're always considering, if you're talking about applying a stress to a system, you're assuming that the system was at equilibrium, and then you apply a stress to that situation that is at equilibrium and ask, how does the system respond? So in all of these questions, you're under equilibrium conditions, and then you apply the stress. Okay. So that's volume. And so the secret to these problems is asking, is the partial pressure changing under those conditions when you're talking about volume? You had a system at equilibrium, then you messed up your system at equilibrium by compressing the container or increasing the container, and whether you added an inert gas, it really always falls down to those two possibilities, that the volume was decreased or the volume was increased. So you have to look at the question and read carefully and say, okay, what's happening to the volume under these cases? And then you can figure out which direction it's going to go. And of course, that was all one example. You have to look at what the particular reaction is, how many moles are on one side and how many are on the other, to think about this. So Le Chatelier also works for temperature. So in this case, you're thinking about what happens if you raise the temperature of an equilibrium mixture. So the reaction mixture is at equilibrium, delta G equals 0, Q equals K, and now you're changing something. You're changing the temperature. So raising the temperature by adding heat will cause the reaction to shift so that that heat is absorbed. So this is the same idea. You're applying stress to the system, raising the temperature. The reaction's going to respond so that that heat that was added is now absorbed. So you go back to where you were when you started. So Le Chatelier's works for temperature as well. It's the same idea, but here the stress is changing the temperature of the system, adding heat or removing heat from the system, and thinking about how that reaction that was at equilibrium is going to respond to this stress. So let's consider an exothermic reaction first. So an exothermic reaction, if we are raising the temperature of an exothermic reaction, you will favor the formation of the reactants. Why is that true? Well, with an exothermic reaction, you're producing heat. And in the reverse direction, you would be absorbing heat. So according to Le Chatelier's principle, you want to respond to minimize the stress. So if you raise temperature, you want to shift in a direction where that heat will be absorbed. So shift then in the endothermic direction. And so for an endothermic reaction, it's just the reverse of this. For an endothermic reaction, you're absorbing heat toward products and producing heat toward reactants. If you raise the temperature of an endothermic reaction, you will favor the formation of products because, again, if you're adding heat, you want to absorb the heat, so it'll shift the reaction in a direction that absorbs the heat. So let's consider this a bit further. In this case, delta H is our predictive tool. If we know delta H, we're going to be able to predict the direction that the reaction is going to go. Before, we were talking about delta G as being our indicator. So here, delta H is telling us quite a bit about what's going to happen, i.e. whether the reaction is exothermic or endothermic. Let's just do a quick example. So here's a reaction, delta H, negative 197.78 kilojoules per mole. Is that an endothermic or exothermic reaction? Exothermic reaction. So if heat is added, if the temperature is raised, what direction will it go? Toward products or reactants? Reactants. So it'll absorb, it will want to absorb that heat, so it goes in the endothermic direction or the reverse direction. So that's pretty simple. Delta H allows us to make that prediction. All right, so we need to think now about the relationship between temperature and equilibrium constants. So equilibrium constant has been constant up until this point, but now we see that temperature will change the equilibrium constant. The ratio of products to reactants that you have at equilibrium will depend on whether it's an exothermic, endothermic reaction, and how much heat is in the system, the temperature that the reaction is being run at, you'll get a different equilibrium constant, a different ratio of products to reactants if you're at one temperature versus another temperature. And also, we'll come back to this at the end of the course, reaction rates also depend on temperature. So how fast those reactions go depends on temperature as well. All right, so now we want to figure out exactly how equilibrium constants depend on temperature. And to do that, we have to think about what we know in terms of equations that have temperature in them and have equilibrium constants in them. So we know that delta G naught is minus RT natural log of K. We also know that delta G naught is equal to delta H naught minus T delta S. So now if we want to take that information and combine it and solve for the equilibrium constant in terms of delta H, and we want to do that, we want to solve for it in terms of delta H and in terms of temperature, because we want to think about delta H, endothermic, exothermic reactions, and the relationship between equilibrium constant and temperature. So if we just rearrange these equations that you have already seen and should be reviewing now for exam 2, you can come up with this. And now we want to think about which of these terms are temperature dependent. So I've already told you that the equilibrium constant is temperature dependent. Delta H here and delta S, we can assume that they're pretty much constant over any temperature that we would be looking at, any temperature that a reaction would be run. So these guys are not really changing. And so if they're not really changing, then we can see that the equilibrium constant is going to change with respect to the change in temperature. So as we change temperature, K will vary here. And we can look at this for two different temperatures. So we look if you change the temperature of the system, the first temperature and the second temperature, T1 and T2. And both, there'll be different equilibrium constants at these two temperatures, different ratios of products to reactants at these different temperatures. So if we write out two equations then, one for K2 with T2, so the equation for the second temperature and the equation for the first temperature at T1 and the first equilibrium constant for that particular temperature. And then if we subtract these two equations, so if we subtract the natural logs of the K's, we can express that in terms of natural log of K2 over K1. And if we subtract the second part, when we subtract this from this, the delta S over R terms are going to cancel out. They're the same. Delta S is not changing with temperature here. And so those two terms would be the same. They're going to go away. And now what's different, these two temperatures, and we can pull out the negative delta H here. We can pull out the 1 over R, and that leaves 1 over T2 minus 1 over T1. And it has a name, so you know this must be an important equation. That's partly how you can tell, is the Van Hoff equation. So it tells you how the equilibrium constants are going to change with temperature. Now let's look at how the numbers are going to work out if we have a negative sign here, i.e. if it's an exothermic reaction, or we're going to have a positive delta H, so that would be an endothermic reaction, and whether you're adding or removing heat, there'll be a difference in the ratios of K1 to K2. So let's think about what comes out of this equation and rationalize it. So this looks a little complicated, but it's actually pretty simple. So here all we're doing is saying, what if delta H is negative? If delta H is negative and we have T2 greater than T1, well, this negative sign here is going to be negative all the way through here. It's always present. That's part of the equation. Delta H now, if it's negative, you'll have a negative here. And then we consider the difference between 1 over T2 and 1 over T1. And in this case, if T2 is greater than T1, that's a negative. So when you multiplied all those out together, we would have a negative here. And that's just what's all done there. Now let's rationalize that this makes sense. So this is just the same thing, but has a little more rationalization in it. Puts things in words instead of using the greater and less than thing. So for the case where, and these parts aren't written in your notes, but if you want to add the words to it, that's fine on the handout. So, and you can just think about this on your own as well. So if delta H is less than 0, negative number, you have an exothermic reaction. So what happens if you increase the temperature of an exothermic reaction? And let me just put those back up on the board for a minute. So for an exothermic, it's not the best chalk. For an exothermic reaction, we're talking about reactants going to products. In an exothermic reaction, heat is produced in the forward direction, and heat is absorbed in the reverse direction. So if we increase the temperature, it's going to want to go in a direction to compensate for that, to absorb the heat. So it's going to go toward reactants. And so you're going to have a K1 that's greater than K2, which means at the new temperature, you're going to have less products or more reactants. So we can rationalize what that would be true. And if you don't want to rationalize it, you can always take the Van Hoff equation and figure it out by looking at the different signs and what it would mean, what's going to happen in terms of that ratio of K1 to K2 when you have this particular condition. Now, if you decrease the temperature of an exothermic reaction, then it wants to compensate by producing more heat. You've decreased the temperature. It wants to respond to the stress to minimize the stress. The way to minimize the stress is produce more heat, so you'll make more products. Now, for the endothermic reaction, it's just the other way around. So reactants going to products. Here, heat is absorbed. And in the reverse direction, heat is produced. So now if we have our endothermic reaction and we increase temperature, we're going to shift toward products, because we're going to want to absorb that heat that was just added, minimize the stress. And for an endothermic reaction, if we decrease the temperature then, we're going to shift it to produce more heat, i.e. toward reactants, so we'll have less products. And we'd have K1 that's greater than K2. So you can use the Van Hoff equation to rationalize the prediction of change, or if you're given numbers, you can say the exact amount of change. If you're given a K value at one temperature and then said, okay, if we change this temperature, if we increase it, this is what delta H is. What is our new equilibrium constant? So you can use the Van Hoff equation to come up with direct numbers, or you can use it to just rationalize the direction of change. If you have less time on a test, you can also just think about what might be going on here and predict without working through the numbers. Okay. So now we're going to apply what we just learned to think about how it can be used. So you want to think about the shifts that we talked about last class and the ones today. Have options of adding and removing products or reactants, changing volumes, changing temperatures. This is quite an important reaction. And we talked about this last time. nitrogen gas plus hydrogen gas going to ammonia. It's an exothermic reaction. So if it's exothermic and you want to drive it toward ammonia, which is what people do, they want to make ammonia, they want to what's called fix nitrogen. So ammonia is used in fertilizers, lots of nitrogen in the air, but you don't want it in the air, you want it in your soil for growing better crops. So you want to do this reaction. If you want to maximize the yield, then it seems like the low temperature would be good. It's an exothermic reaction, so low temperature would be good. It would favor products. But there's a problem with that, which is that low temperature also slows the rate. And you usually want a good rate. You want to make a lot of products pretty quickly, make some money off of it. So you have to balance here. So sometimes the thermodynamics and the kinetics are working against each other. What would favor one doesn't work so well for the other. So they have to have a compromise temperature, which is actually quite a high temperature of 500 degrees Celsius. All right, so it's a little bit of a problem there. The temperature thing isn't working for us. What are some other things that they could do to drive the reaction toward products? What else could you do? Okay, what else could you do? I'm hearing a couple different things. I'm looking for one others. What about? So a couple things that you could do that would work. I think I heard most of them now. Remove products as they're formed. So if you remove this product, that would drive it toward more products. And so one thing that they actually do is every once in a while to stop the reaction, cool it all down and liquefy the ammonia gas. The liquid pours off, and then you've removed this product, and then you make more product. So if it reaches equilibrium, you pull off the product, and then it makes more. And I also heard about this, compressing the volume of the container, because over here, the reactants, there's 4 molecules that are reacting to form 2, and so that should also help shift in the correct direction to make product. So they actually do these at this pretty high temperature, and they have to apply a really high pressure to compress that volume. So this is expensive. It requires a lot of energy actually to do this reaction because the conditions that are required to maximize the yield. So again, why this is important, there's lots of nitrogen in the air. However, it's really stable. And you could probably tell me why it's so stable if you draw a nice Lewis diagram of this. It's difficult to break these apart. So that's why this is a hard problem, because you want to break this bond to have usable nitrogen. And it's challenging to do. So that process which I just described to you is one that was developed, developed quite a long time ago. This reaction is called the Haber-Bosch process, and it's responsible for generating 1.6 times 10 to the 10 kilograms of ammonia each year in the US for fertilizers and other things. And it was developed by these 2 men right here. Haber came up with the initial idea, and Bosch helped figure out the appropriate conditions to get the maximum yield. So all they're doing is basically using some of the principles that you've already learned in this course, and they both won Nobel Prizes for being part of this process. This one initially and this one later on. I'll also mention this is an interesting man if you're interested in sort of history of science. He's a German chemist. And during World War I, he switched his effort from fertilizers to coming up with different kinds of poison gases that could be used in warfare. But he was not rewarded favorably for this later on because he was also Jewish. So in 1933, he had to flee Germany despite all that he had done for the war effort earlier on. And he did not live too long a life after that. But this was developed a long time ago, and it is still used. So some scientists are actually trying to figure out how to do a better job. They figure any process that was really started to be developed before in the 1800s and kind of refined in the 1900s, maybe we could do better. Again, a lot of energy is responsible, high temperatures, these extreme pressures for the condensed volume. Maybe we could figure out a way to do that same reaction without those extreme conditions that require a lot of energy. And so a number of scientists have looked to an enzyme, a protein found in bacteria. It does the exact same reaction as what is done commercially, but it doesn't use any high temperatures or any high pressures. So a number of scientists are trying to figure out how this protein works, how it's able to do this reaction so efficiently. And here's a space-filling picture of the enzyme. And here are metalloclusters that do the actual chemistry. And so an orange is iron and yellow is sulfur, blue is nitrogen, red is oxygen, gray is carbon. This purple color here is molybdenum. So these are metals used in biology to do particular kinds of reactions. And this just shows the, a little bit more about the cluster is sort of in the heart of this protein molecule, and all the chemistry happens at the metals, but it's surrounded by a lot of protein. So that's one effort that a number of scientists are venturing on. Often we find various forms of bacteria have proteins that do reactions that we want to do, and they do it much better than we do them. And so we want to understand how that works. And this is one example. Turns out this is quite complicated, and scientists still don't understand the exact details of the reaction mechanism at that metal site. Another attempt is just to pretend that, to move away from nature, and Dick Schrock's lab here at MIT has been able to do this reaction using a sort of designed catalyst that has molybdenum in the center. And you probably have heard the name Dick Schrock because he won the Nobel Prize in Chemistry just a few weeks ago. So he didn't win for this. This is another one of his contributions. All right, so okay, really quickly, I want to give this one more biological example, and then we'll hear more about exam 2. So again, as I will emphasize in this course, all the things you learn can be applied to biological systems as well, same basic principles. So here we have hemoglobin. So hemoglobin is the protein in your body which carries oxygen, carries oxygen from the lungs to the cells. And you can write the reaction for hemoglobin and oxygen the way you can write any of the reactions we've written. So hemoglobin plus oxygen goes to oxyhemoglobin. So here, this is just oxygen bound to the hemoglobin. Now let's consider what happens if you decide to climb a mountain. So the partial pressure of oxygen is different at sea level, it's higher, than it is in the mountains. So as you go up higher altitudes, the partial pressure of the oxygen decreases. So what does this mean in terms of this equilibrium? Which direction would it shift? If this is decreased, partial pressure of this is decreased. Yeah, so you're going to shift toward reactants, which means you have less oxygenated blood. You have less oxygen bound. And that's not good. It makes it much harder to get energy to climb that mountain. So that's not good. So usually, if you're going to go climb a mountain, you have to adjust. You have to acclimatize. And so I don't know, how many people are mountain climbers? Anybody? A few people. So you usually have to get up and wait for a while before you can start climbing. And what actually happens is your body's making more hemoglobin. So you have to wait for this to happen. And if it makes more hemoglobin, what direction does it go? Right. So it shifts toward products. So then you're in better shape to climb your mountain. So again, same principles of shifting reaction applying to a biological system.